Okay, welcome back again, and this is the Chipmaster, and in this video I'll be doing another laptop repair here on a laptop itself. It's an Acer machine, and it says no display. As you can see, turns on, no display. Right, my tech was working on it yesterday, and he said that it was a bit tricky for him, so he left it on his desk there for me to look at it. Right, so it's an Acer Aspire 7750. It's an Acer Aspire 7750Z series, and it's not displaying anything on the screen, he said, and it is written here, no display. So I'm going to see if I can repair. Okay, so as I said before, as you can see, it's already disassembled. It's a very large laptop. It's a 17-inch machine. Alright, so I'm going to plug in the power. Right, I'm going to give power. Alright, so I'm giving power. Alright, so I'm going to trigger the board. Alright, this is the power connector right here. So I'm going to trigger the board. Nothing coming in. Connector is plugged in, yeah. Okay, we have 50 milliamp now, as you can see. So I'm going to trigger the board. Alright, so as you can see, I'm taking 830 milliamp, 790 milliamp. Right, the fan stop spins. It's now at 800 milliamp. Right, and the screen is connected. Alright, so I'm going to go again. These ports are a bit loose. Alright, turning it on. So as you can see, it's on, but there's no image. As you can see there, I'm taking 780 milliamp, but there's no image on the screen. Blank screen, and the current is now stuck at 780 milliamp, and there's no image. Right, he tried several RAM and it didn't work, so he handed over to me to see if I can repair it. Alright, so I'm going to move the power. And take out the board. I also need a DC jack, so I'm going to remove the DC jack so I can check voltage and signals. Alright, so I don't have to check all coils because it's not a shorty, it's not a dead laptop, it's powering on. and based off the current judgment, I'm getting good current, right? I'm going to do some inspection, visual inspection on this board, starting from the PCH section here. This is a HM, this is a BD82 HM65, which is the second gen, the 6 Intel Series 6. See, so it's BD82HM65, and that's the Intel Series 6 PCH. This is called the Cougar Point, right, which matches the second generation of the Intel CPU, which is the Sandy Bridge, right? So this under the CPU, under the heatsink here, is the Sandy Bridge CPU, which is the second generation CPU, right? And it is matched with the 6th generation of PCH, which is the HM65, which is the Cougar Point, right? So I'm, inspecting around this area of the PCH, right? I haven't seen anything abnormal like any liquid corrosion or any burn, right? So this is okay. This section is okay, right? 3 volts and 5 volt section, right? 3 volts and 5 volt section, all okay, right? And this is the charging section. As you can see, ISL 6251, a very old charging chip here, which is used back in 2010, 2009, 2010, 2011, thereabout. Right, this is a filter coil here, another filter coil here to filter out any electromagnetic interference. Right, this should be the RAM power supply coil. All is well. And this is the RAM slot here, DDR3. Another slot here which has a RAM in it already, DDR3. Alright, so this is all good. And the board number here, as you can see, is a LA6911P revision 1.0, and it's manufactured in 2011. Right. Alright, in the CPU, this is the bus power supply section here, right? Alright, this should be the bus power supply. This should be VCC SA, right? 1.0 volts or 0.8 volts, and this is 1.05 volts for the bus power supply and the core power supply for the PCH. All is well there. Alright, this is a regulator. This is normally used to control the fan. As you can see, it's close to the fan connector. So this is the fan PWM drive chip, right, which detect rotation, right, and the speed detection of the fan. And it is adjusted through this PWM IC, which is integrated with that functionality right there. Right, so I'm gonna take a look down in the audio section here. As you can see, this is a Realtek, right, ALC, right, 271X series, right, very powerful audio amplifier IC with that audio amplifier integrated. Right, we have a headphone jack and a microphone jack there. Right, we have USB. All is well there. No burn, any form of liquid intake on this side of the board. So I'm going over to the next side. Starting from the embedded controller, right? This is the embedded controller. It's a KB, right, 930QFA1, right? This is a programmable EC. Sorry, it's non-programmable. This is a non-programmable EC. If it was A3, it would be a programmable, or A4 series are the programmable ones, right? So this is all well. No liquid intake, no burn, anything on the embedded controller there. And we're now over to the card reader. This is the card reader section, right? No problem there. And as you can see, there are not much components on this side of the board, right? This is the charging MOSFETs, adapter input protection MOSFETs, isolation and protection MOSFET for battery and adapter. All is well there. All right, so I can now continue with the repair. And this is the CPU core power supply chip. I haven't seen any burn, no liquid intake, anything. All is well there. Alright, so I need a switch for my power button. Okay, so I have soldered my power switch, as you can see here, because it's going to be a bit annoying to be using the multimeter probes to turn on, because I'm going to need it to check voltage and instantaneous signals. So my trick is normally I solder a wire to the switch pin. So you'd have to use the schematic to find the switch pin, right, for the corresponding boards, in order to find and to solder your switch wire to the correct pin. Alright, so I'm going to plug in the power again. I'm going to check all voltages, yeah. Right, so I'm gonna flip over the board because all the coils are on this side. So you see why it's important for the switch. So I just ground, right? So now I'm gonna ground, right? Fan spins. I'm taking 800 milliamp, right? So I'm gonna check all coils from 3.3 volts and 5 volts. So I get 5 volts here and 3.3 volts. Excellent. 1.0 volts, 1.8. So this is VCC PAL, sorry. This 1.8 volts is for the phase lock loop inside of the PCH, and it goes to the CPU, right? So 1.8 volts is for the phase lock loop, right? For the integrated clock controls inside of the PCH, right? 1.05 volts should be here. Excellent. All right, 1.0 volts or 0.8 volts VCC SA. 0.9. Okay. All right, and CPU core, I have to remove the heatsink. 1.35 volts. This is DDR3, so this is 1.5 volts. Sorry, 1.5 volts. 1.5 volts is there. Great. All right, pin number 1, which is 0.7 volts, which is the voltage reference for the RAM. Right, excellent. 0.7 volts is there. All right, next we need to check for the voltage reference, which is at clock and data 3.3 volts, pin 202 and pin 200. 3.3 volts is there. Excellent. All right, so we have the voltage reference for the RAM. I also have clock and data pull up, right? And I have 1.5 volts, which is the core power supply for the CPU, and the CPU power the RAM power management module inside of the CPU is getting that 1.5 volts. So normally if the 1.5 volts is shorted, then the CPU is definitely broken, right? So this 1.5 volts is going to the RAM module, right, and to the CPU RAM or memory power management inside of the CPU. Now I'm going to check now on the, so I'm getting all supplies, right? So I'm going to check with well, I may use oscilloscope. Yes, I'm going to use oscilloscope, right? So I didn't check reset. So PLT reset is normally the last signal. So when you get PLT reset signal, that indicates that the hard start is complete. Hard start is completed. So I'm going to give power. Right, there we go. All right. PLT reset can be found at pin number 22 on the Wi-Fi adapter here. So pin number 1 is this side, pin number 2. So pin number 22 is the third pin from the gap here, 3.3 volts. Right, so I get 3.3 volts. PLT reset is okay, so the hard start is complete, right? After the CPU gets PLT reset signal, then it will go through the DMI bus to communicate with the PCH, right, to start the soft start, right? So the hard start is complete after the PLT reset signal, right? So after 3.3 volts, PLT reset is coming to the CPU, to the EC, to the LAN card, and so forth. Then what will happen is that the CPU will now go through the DMI bus to communicate with the PCH. Then the PCH now will come to read the RAM, right? So this requires oscilloscope. So I'm going to check with oscilloscope to see if the RAM is going to be read by the CPU through the PCH SM bus. And that indicates to me that once the PCH is read, it's reading the RAM, that indicates that the SM bus and everything is okay, right, with the startup part of the PCH and the soft start section, which is the initialization stage. Okay, so now I have the oscilloscope in hand, right? So I'm going to put my probes here on pin 202. Right, so I'm going to give power. Take a look at the screen to see if the CPU is now initializing the soft start. Right, so once you get the signal, that means the CPU gets the reset signal. It's communicated, it has made a communication to the DMI bus to the PCH. The PCH will now go out to check RAM. Alright, so I'm going to give power. Alright, so sorry, I give power. Switch. So as you can see, I'm not getting a reading here. So let me try again to see if I'm actually on the correct pin. Pin 200 or pin 202, any one of them is fine. Alright, so I'm at pin 200. Alright, I give power. Switch on. As you can see, I'm not getting a pulse. There's nothing going on there. Right, so the CPU did not run code here. Right, so normally should be 3.3 volts on both pins. Alright, so I'm checking 3.3 volts. pin 200, I get 3.3 volts. Pin 202, 3.3 volts, right? And pin 204 should be 0.7 volts also, right? So I'm getting, this is the RAM termination, right? Pin number 1 here, which is the voltage reference, right? So it's 0.7 volts at pin number 1 and pin number 204, but the RAM is not read. So the RAM is not read. So normally the BIOS can cause it, right? Or a bad CPU, or it could be the PCH itself, right? So to eliminate, we normally flash the BIOS first. So I'm going to flash the BIOS. Okay, so I have now downloaded the BIOS, and I'm going to save it. I have created a backup, so I'm just going to name this as a backup. Alright, so I'm going to save it here. So I've downloaded the BIOS here. I will save, right? Alright, so this is the backup. I've extracted the downloaded file. I've extracted the downloaded file here. So I'm going to open the backup. Alright, so this is the backup. As you can see, it starts with 5AA5F0, so that's a UEFI BIOS. Alright, so I'm going to open the one that I've extracted from the official website. And here is it. As you can see, this is a inside BIOS, right? So I will see if I can extract. So as you can see, this is my BIOS image. This is a BIOS.fd, which is a 4.2 megabyte in size. Alright, so I'm also going to drag that into the hex editor, which is WinHex. Alright, so I'm going to search for my string, my hex. Alright, so sorry. Alright, so I'm going to search for the hex file, which is a 5AA5F0. As you can see, my starting string is here, right? And it is compared with my backup, right? So this is roughly 4 megabytes. Alright, so as you can see, it is 4 megabytes in file size. So I'm just going to save this. I'm going to jump, right? So I'm going to start from the current position, and I'm going to fill this with 3, 1, 2, 3, 4. Okay. Let me start over. Go back. Alt G from the current position. One more F. Sorry. Alright, so the backup file, as you see, the ending file is here. Alright, so another technique I normally use. Alright, so this ends with 0F09, 0F09E9. So I'm going to go back. Another method I'm going to use. Right, so I press Alt 1. Right, so I'm just going to search for that hexadecimal. Control-Shift-C. I'll paste that there, and that's the ending of my string there. And I press Alt 2, right, Control-Shift and N, and save this as a new BIOS. .bin. Am I recording? Yeah. So that's done there. So as you can see, my new file size, my new BIOS is also 4 meg, right? And my backup is the same. All right, so okay, so as you can see, so my new BIOS here is 4 meg. It's the same size with my backup, and it's identically the same, as you can see. All right, so this file is ready to be programmed into the RAM. All right, so I'm just comparing the size and the characters and make sure that they are the same. Alright, so this is ready for program. Alright, so I'll program and get back to you. Okay, so the program is complete, verification okay. Alright, so I'm going to head over back to the camera. Alright, under the microscope, I will now solder back this ROM chip to the board. Right here's the spot. Alright, so I'm going to check on those pins from the RAM, pin 202 or pin 200, N1, and I will see if I am getting anywhere with this. Alright, so I will check in on the RAM slot. Yeah. So the BIOS is now out of the way. Hold on, I think I'm making a bridge here. Should not have a bridge. Like when I was testing it the first time. It created a bridge. Alright, there you go. Alright, so I'm gonna check at the pin. Is that a bridge? No, it's not. Alright, so I'm gonna check there now. Alright, I'm gonna give power. Oops, need to find my switch. Alright, so I give power. And it's the same phenomenon. Right, there is no waveform, so it's not the BIOS. Same phenomenon. Oops, 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 oops. I see wave. I see a waveform. Did you see that? I didn't get any wave before. Now I get waves. I wasn't seeing it clearly. Hold it. On one side I get wave. Or did I get a wave? So this pin is pin 202 and this pin is 200. So let me check again. Oh, so I get a waveform on pin 200, but pin 202 there's no waveform. Let me try again. Let me check the pins if there are any bridges. If any of the pins are touching. And I have no touch. They are not touching. No grounding. So I think I found my problem. Normally these are pulled up by a MOSFET. So these signals are passed through two N-channel MOSFET. They could be composite, they could be separate. On older boards than some desktop boards, most desktop motherboards use them as separate depending on the manufacturer of the motherboard. So I'll have to check these MOSFETs with the help of a schematic. Alright, so I'm going to check one more time just to confirm, because I'm getting a wave on one pin, on pin 200, but there's no wave on pin 202, which is the clock. So I'm getting data but no clock. Right, so definitely the CPU can't be able to read the RAM. Right, the SM bus is used to read the parameters of the RAM, such as the manufacturer, the speed of the RAM, right, the read and write access speed and so forth of the RAM. Right, so I'm gonna check on pin 202 again. Alright, pin 202. I'm gonna check if I'm getting voltage again also. Alright, so I give power. Sorry. Hold it, sorry, let me. Yes, I'm on the right spot. No waveform. Alright, pin 200. I got a wave. Let me check the other slot. Right, it's right here. Right, pin 200. Pressing the switch. Hold it, my wire is out of order. These wires tend to have a break somewhere. For the DC jack, there's a break. Let me, alright, going again. Alright, pressing the switch, pin 200. I got a wave, excellent. Alright, pin 202. I got a wave. I got a wave on these two pins. I got a waveform, but there's only one. So let me try the RAM in this pin. So I'm going to try the RAM in this one. So I'm going to try the RAM in this slot. Right, so I give power. Pressing the switch. I get 830, 800 milliamp, 780 milliamp. It's the same thing, getting a stock current. Connecting the keyboard. No caps lock is there. No caps lock, so it's not posting. Let me see the RAM. This is a PC3L. I don't think this RAM is compatible with it. Let me try another RAM. A DDR3 RAM I need. Let me pause. Alright, so I'm trying a DDR3 RAM. Alright, so I'm giving power. 600 milliamp, 690, 650, 660. Doesn't seem right. Connecting the keyboard. Not getting a caps lock. No caps lock there. Okay, so I have already tried RAM and it's the same thing. So now I'm going to check on the EC, right? And I'm going to check the LPC bus, right? The LPC bus is the communication line between the CPU and the PCH, right? So the LPC, which stands for low pin count, which is going to be able to allow the EC to communicate with the PCH, right, through that bus, right? So LPC, you have LED 0 to LED 3, that's 4 lines, right? And that is LED 0, LED 1, LED 2, LED 3, and LPC frame. So the LPC frame, which is the main signal in which the PCH will use to communicate, vice versa with the EC, right? And if you get wave and there is no voltage, if you get voltage, sorry, and there is no wave, there is most likely something wrong with the CPU. So I'm going to do that now. So I'm going to head over to the schematic. Okay, so I'm now on the schematic. All right, so here it is. So as you can see, it's a 7750, which is this model. All right, and we have the Sandy bridge here, right? So this is the second generation of the Intel CPU, which matches the Cougar point that I said before, which is the HM65 or the Intel Series 6 PCH. And here is the LPC bus, right? So the LPC bus is the communication line between the Cougar point, which is the PCH, right, and the embedded controller, right? So I'm going to go to the embedded controller, and the standby name to get to this page for this chip is AVCC, which is the standby name for the embedded controller. As you can see, AVCC. So this is the LPC and miscellaneous section. So I'm going to check on pin number 4 here, right? So I'm going to check if I'm going to get 3.3 voltage here, 3.3 voltage here, and all the way up to LED 0. So it's 4 bits, 0, 1, 2, 3, and we have frame, right? And I'm going to check on that line here, pin number 4. All right, so pin number 4 should be 3.3 volts. I'm going to head back over to the camera. All right, so I'm going under the microscope as well. All right, so I'm going to check pin number 4. All right, so this is the EC. All right, so we have pin number 1 mark here. All right, so this is pin number 1, 2, 3, and 4, right? So pin number 4, I'm going to connect the power. Alright, so I'm going to give power. Alright, so take a look at the screen on the oscilloscope. Alright, so I'm going to give power for pin number 4. Sorry, I'm going to check for voltage, sorry. So I'm turning on the unit. Alright, it's on. I'm getting 70 milliamp, 670 milliamp. Alright, so pin number 4, 3.3 volts is there or not? Yes, 3.3 volts is there. Pin number 5, 3.3 volts. Excellent. Pin number 6, or pin number 7, sorry, which is LED 3. Right, pin number, so it's pin number 4, 5, 7, 8, and 10. Pin number 4, 5, 7, 8, and 10. All should have 3.3 volts. Right, pin number 4 is 3.3. Pin number 5, 3.3. Right, pin number 7, 3.3. Pin number 8, 3.3. 9, 10, 3.3, all is well. So the voltage is there. So I'm going to check this for a wave. We should get about 3 to 5 jumps and continuous jumps. So take a look. So as I'm taking on LPC frame there, I'm not getting anything. Let me go again. As you can see, pin number 4. Go again. I get 1 jump there. It's supposed to be jumping effectively. I only get 1 jump, so that means we are not getting a proper communication with the CPU. Right, so I'm going to check on pin number 5. LED 0. LED 3, sorry. Alright, let me go again. What is that? Pin number 5. 1 jump. That's abnormal. Right, pin number 7. Alright, I give power. No jump. No jump. Alright, let me try again. Just making sure that that my oscilloscope is working. Alright, it's working. So 5, 6, and 7. So it's 5, 6, 7. I give power. That's abnormal. Right, pin number 8. Let's go for pin number 8. That's 5, 6, 7, 8. Let me try pin number 8 now. I get 1 jump. That's abnormal. Right, and then 9 and 10. I give power. No jump. So I'm not getting a jump. That's abnormal. So I'm not getting a proper communication with the CPU. Let me pause. Okay, so as you can see there, I'm getting an abnormal reading on the LPC bus. The voltages are okay, but there is no wave. Right, so you have to make sure that when you're checking, you should check the LPC bus, right, and see if they're getting proper communication on the LPC bus. Right, so if there's voltage and no wave, then there's a problem with the CPU. So I'm going to try another CPU. Alright, so I'll try another CPU. Alright, so I'm going to get another CPU now. Alright, so I now have it's a Pentium CPU. Right, so this one is a Pentium. I'll try another Pentium here. Alright, so alright, so I'm gonna plug in the power, going back to the LPC bus. Alright, so I'm going to go back into the microscope. Alright, so getting the oscilloscope ready. Alright, so pin number 1. Pin number 4. Alright, so I give power. Pressing the switch, turns off. Alright, so I get 1 jump. I'm getting some jump there. Alright. Pin number 5. Alright, so I get in 2 jumps there. Very good. Alright. See? There we go. There we go. We have more jumps there, as you can see. Right, so let me go again. Right, so LED 0. That's LED 0. 3, sorry. Alright, this is LED pin number 7. LED 2. That's LED 3, sorry. So this is LED 2. Alright, we have a jump. Shuts down because the RTC battery is out. Turns on. There we go. There we go. Yes, we have a sequence of jumps there. Right? That's pin number 7, 5, 6, 7, 8. Sorry, that's pin number 7, 8. Alright, that's LED 1. Alright, so shuts down. Right, the RTC battery is out, so that is why it's going to power on. Alright, there we go. We have a sequence of jumps there, and that's good. Very good. That's what I want. Alright, checking pin number 4 again. LPC frame. Alright, so I have 1 jump. Alright, going again. Okay, 1 jump. Let's check pin number 10. LED 0. Alright, so I have a jump there. Alright, there we go. There we go. So as you can see, there's a difference there with the jumps. Now I get a sequence of readings, so that pull down. So each time the CPU is communicating on the LPC bus, it is pulling the line to ground, and that's actual communication. Right? So it's not a continuous communication until there's an interrupt. There's an interrupt signal, right, which is called the SERRIQ, right, which is a serial interrupt. So that is going to use to the EC will talk to the CPU through that line in order to communicate and to tell the CPU. It's like an addressing signal to address to the CPU that it needs an attention to do for the CPU to do a specific task, right? So that's when there's going to be actual jump, right? But for the first time and turn it on, it's going to read and communicate with the LPC bus. If the EC needs to address the CPU, it will address it through the serial IRQ line. Okay, so the jumps are pretty much fine now. So I'm going to connect the keyboard. So the keyboard, I'm going to get the keyboard. Yeah. Alright, so I give power. Alright, so I'm turning on. Alright, so let me see if we get caps lock. Yes, there we go. There is a caps lock there. And we have a beautiful caps lock there, as you can see. Yes. And the job is done. Alright, so I'm going to assemble the unit inside of the case here. And then I'm going to do another test to see what's the outcome. Okay, so I now have the board partially assembled inside of the case. Alright, because of the width and this laptop is so big, so I'm going to use the other camera. Alright, so should be able to see. Alright, so I'm going to give power. Alright, I have power, like switch. Alright, so it turns on and off for about a second there. Let's see. There we go, we have Acer. Alright, this port is a bit loose. Let me go again. There we go. Alright, so I'm going to there we go. Alright, so it's no bootable device. Alright, please restart the system. Alright, so that's completed there. Alright, so I hope you enjoyed the video there. Hope you learned something. Alright, so in another video I'll repair something for you. Alright, so I'm just going to conclude the video now. So bye.